So today's webinar is titled Introduction to LimitState Slab, and it's going to provide you with an overview of how you can apply our new Yieldline software, LimitState Slab, to a wide range of slab analysis problems. The topics today are an introduction to the software presented by Professor Matthew Gilbert, followed by some of the theory and practical application of LimitState Slab to a range of slab analysis problems, which will be presented by myself. As always, the webinar is due to last about an hour. We'll include a few minutes at the end for some questions. These can be posted via the question functionality that should be present in the webinar interface that you have in front of you. We do try to answer as many of your questions as we can in the time available, but this isn't always possible. So if we don't manage to get around to yours, then do apologise in advance. Obviously, if you do have a technical question that might take some time to answer, you're more than welcome to contact us outside of the webinar via info@limitstate.com, and we'll be happy to answer these in detail for you. So without further delay, I'd like to welcome you to our first speaker today, who is Professor Matthew Gilbert, who'll be speaking a bit about the methodology. I'll pass you over to him.
Thanks very much, Tom, and thanks very much to all of you for joining the webinar today. Okay, so when we think of Yieldline analysis, we tend to think of the simple failure mechanisms of the sort you see on the left of the next slide, showing on the screen. So the key thing is that Yieldline analysis works extremely well if you have simple geometries, simple loading conditions, and simple simple scenarios effectively. The two images on the right show more real-world examples where it's very difficult to identify a Yieldline pattern by hand. And the key thing is that if we have a general numerical tool, which is what we've developed in LimitState Slab, then those kind of geometries can easily be dealt with as well. And also, as well as applying uniform loading, we can also apply arbitrary patterns, point, patch, and pressure loading in combination. And we can see now on the next slide animations of the mechanisms. Okay, so just before we get into the meat of the webinar, just a few words about the company LimitState. It's actually a spin-out from University of Sheffield in the UK. Been around for almost 10 years with the goal of making available techniques developed in academia for engineers and providing engineers with powerful ultimate limit state analysis and design software. And the key kind of feature of the products that we develop is that they incorporate state-of-the-art optimization techniques. And as a commercial operation, we're clearly committed to ensuring the software is easy to use and fully supported and robust and well validated. The current time, we have three main products: so LimitState Ring for masonry arch bridge analysis, LimitState Geo for geotechnical problems, and now the most recent addition, LimitState Slab for concrete slab analysis. And this software is used widely in the UK and also in 30 countries, more than 30 countries worldwide. I'll just give you an indication of the kind of organizations that are using the software. We've got just an extract from the website, and this is the A section, so big companies, ACOM, Arup, Atkins, and so forth. In terms of our motivation, if you look at the engineering analysis space, it's very clear that if you want to do a linear elastic analysis, you're very well served. The finite element method has made linear elastic analysis convenient and mainstream. The same, however, can't be said if you want to do a collapse analysis. So rigid plastic analysis tools, which are effectively the equivalent type of tool when it comes to looking at failure, and much less well developed. And for many years, engineers have had to put up with hand calculations or automated hand calculations. In case you're not clear what I mean by rigid plastic analysis, well, effectively it's a direct means of calculating the maximum load sustainable by a body or structure, and we tend to use a simple rigid plastic material discretization. And the benefits as far as end users are twofold. When you're using these tools in design, you tend to find that you end up with more economic solutions than with elastic methods. And if you're looking at this from an assessment perspective, you can find often hidden reserves of strength in existing structures. And so just to kind of put some of the points I've made already together, if we're looking at existing tools in the engineering analysis space, for collapse, we're typically talking about either hand calculations or automated hand calculations at one extreme, or much more complex methods, for example, based on nonlinear finite elements at the other, with a major gap between those two types of tool. And what we're focusing on doing is filling that gap with mainstream analysis tools based on rigid plastic analysis. And this can be applied in the geotechnical engineering space, so slope stability type problems. It can certainly be applied in the masonry arch analysis space, and also clearly of interest today, it can be applied in the concrete slab analysis space. So if we move on then to the traditional method of analysing concrete slabs at the ultimate limit state, the Yieldline method, just a few words about that. It's actually a very long established method. The term Yieldline was first coined in a paper appearing in 1923 in the Structural Engineer. Johansen, a Danish engineer, then developed the theory that underpins the method, and it was later shown that the Yieldline method is really an upper bound plastic analysis method. Calculations involved in the Yieldline method quite simple. Typically we'll use a work method where we're equating internal work done at yield lines in the slab to the external work done by the applied load. And often, if the mechanism is simple at least, the calculations can be done very quickly and easily. So advantages of the method are simple and easy to use, and you can get very economical designs or realistic assessments of slabs. The downside is that you must choose a realistic mechanism. If you choose an incorrect mechanism, then you will get an overestimate, so a non-conservative estimate of strength. And another downside is that it only considers flexural failure. So it doesn't consider, for example, serviceability, limit state, and it doesn't consider rudder failure modes, for example, punching shear. In the last couple of decades, there seems to have been renewed interest in the Yieldline method. One example of this is that Middleton and co-workers at the University of Cambridge used the Yieldline method to reassess a large number of concrete slab bridges which had been condemned as being substandard or unable to carry modern vehicles when elastic methods were used. So on this slide you can see the assessed capacity for 21 bridges. The red bar shows the elastic assessment, the green bar shows the plastic assessment, and in very many cases the green bar shows that the bridge can actually carry 40-ton vehicles, which is the required capacity for vehicles currently. The way this was done was by effectively cycling through a series of potential failure mechanisms, finding the most critical, and then outputting the result. And you can see there's actually 27 mechanisms shown on the right-hand side of the screen. I guess the big issue is that if you're dealing with a non-standard geometry, perhaps there's another failure mechanism which isn't on this list, which wasn't analysed, and so if that's actually more critical, you end up with a non-conservative estimate of strength. Another instance of Yieldline method being used in the last few years is for the Cardington European concrete building that was constructed 15-20 years ago. And what they did was they used different design methods to design different floors. And what they found was that the Yieldline design method had significant advantages, both in terms of the amount of reinforcement that was indicated to be needed, and also the number of bar marks. So the simplicity of the design from a kind of a constructability perspective was also good. So it looked to be a very, very promising method. And what they did at that time was they produced a design guide, and in the preface or in the foreword it says, Yieldline design is so easy once you know what you're doing. And the big issue is that not enough engineers have felt confident to use the Yieldline method as a hand method because of the concern that a critical failure mechanism is being missed. So what we're going to do today is show you that software, the LimitState Slab software in this case, can now be used to automate that process and really hopefully make Yieldline analysis a mainstream tool once more. So I'm going to now hand over to back to Tom Pritchard, who's going to talk you through the software and then actually explain how the software works internally, how we actually get the answers that are shown. So I'll just pass you over to Tom now.
Thanks, Matthew. So I think the easiest thing to do is actually just open the software and start with a bit of a simple problem. So you can see here that we've just got a blank grid to start with, and what I'm going to do is just create very quickly a non-standard slab geometry and apply some loading and solve it, just to show you how the software works in practice. So all I need to do is draw the shape of my slab, and we'll make it quite an irregular shape like this. So you can see now that this solid zone has been created. So we've got a geometry. Then all I need to do is add some material properties. So if I add this unit MP weightless slab definition, just drag it onto the problem like that, that's now assigned that material to the slab. The next thing we need to do is add some boundary conditions, because at the moment there's nothing actually supporting the slab. So if I select the entire thing, and then in the property editor here on the right hand side, select the external boundaries and set them to be simple. So now we've got a geometry, we've got the slab definition of the material, and we've also got some boundary conditions. So the last thing that we need to do is actually apply a unit pressure loading in this case. And to do that, what I'll do is just click on this button up here, and it'll allow me to add a new load. And I'm just going to say select all, which is just this one zone here, and OK, and it's going to add a unit pressure load to it. So if I just turn off the grid, you can see here we've got all the things now that are necessary for a simple slab analysis for this irregular geometry. So we've got, again, the geometry, the material, the loading, and the boundary conditions. So now all we need to do is click solve, and you can see that the software is going through a range of solutions until it finds the one that is actually critical for this case. And what we can do, and what we saw slightly in Matthew's presentation at the beginning, was that we can animate the slab deformation to get a better idea of what's actually happening at the point of collapse, and we can rotate that and have a look at it. So you can see here what's going on at the collapse state. And then what I'll do is I'll just return it back to 0, and you get the yield lines back again. In the output window at the bottom here, you can see that the solution in numerical terms is stated in terms of an adequacy factor on the applied load, and in this case it's 3.85, and that means that the unit pressure loading that we have applied to the problem can be multiplied up 3.85 times before collapse is going to occur. So That's without any partial factors or anything. We've got basically a straight factor on the loading of 3.85. So going back to the actual presentation, is how do we actually automate the Yieldline method? So lots of people have actually tried to do it. In the early 1970s, Henry Chan from Oxford tried a rigid finite element approach where he specified the problems as being made up of rigid finite elements with potential yield lines existing along the edges of those finite elements. So you can see here on the left hand side where this red line is, and the problem was to optimize the solution to find the critical arrangement of those yield lines. Now that's all very good, but in this type of analysis, the problem is the topology of the elements has quite a big influence on the outcome of the analysis. So you can see obviously on the right hand side here, the elements are arranged very differently to the ones on the left, and for the same problem you're getting a very different solution. And for things where for slab analysis in particular, if you've got things like a fan mechanism that you may expect underneath a point load, then you would need to have your elements prearranged in a radial mesh, for example. Otherwise it would be difficult to actually identify a fan type mechanism. So it was good, but there were issues with it. Then actually must have moved past it, but one of the developments in the 1990s was based on the Chan method, and it took that as an initial solution and then looked to move the nodes, and that's what Johnson did in 1994. But we found that he still couldn't actually identify these fan type mechanisms, which were quite prevalent in slab analysis problems. So later on, in sort of the 2000s, 2010s, we at LimitState came along and realised that there are other numerical methods that could identify these fan type layouts, and it was very much based on work in the truss layout optimization field that was sort of spearheaded by Dawn and others in the early 1960s. And just explain the method here. What you see on the left is that we've got a potential design domain for a truss with support conditions, so a pin at the bottom and a pin roller at the top, and a loading applied. And the truss layout optimization problem for this was to sort of flood the design domain with nodes, and those nodes could then form the ends of potential bar elements, so ones that may want to exist in the critical solution. So you can see here actually it's a simplified version of the left hand one here, so we've got less nodes in it, so we've only got 4, and all of the nodes are connected to each other. And the job for the truss layout optimization is to identify from this set of potential bars those that make up the sort of least weight critical topology. So you can see here it's 3 bars, 2 of which are in tension and 1 of which is in compression. And the more nodes you start off with, the more potential bar elements you have, and therefore the more complex the final optimized structure can be. So you can see here for a problem that's the same but with a lot more nodes actually added to it, that the solution obtained is a lot more complex. Actually it's a quarter of a bicycle wheel, and it doesn't take a great leap of logic to see that a quarter of a bicycle wheel is actually identical in topology to a quarter of a fan type mechanism that you may get in a slab analysis problem when you're using yield lines. But obviously the loading that you apply in a truss optimization problem is not necessarily the same as one you might think about for a slab problem. So what we do is actually think, instead of an externally applied loading for the truss, we think of it as a self-stress or a pre-stress problem. and then you can actually simulate the full fan mechanism as you would associate with the applied point load on the slab. So you can see here is if we apply a self-stress and have the same sort of large amount of nodes to the initial design domain when we're solving it, that we get this nice fan type mechanism. So just a little bit about the actual mathematics behind it. Basically, the formula for the truss layout optimization is basically saying that we want to minimize the volume, and the volume is essentially the sum of the lengths times the areas of all of the elements that exist in that optimum structure. If you rearrange that slightly, you can make it into terms of length over yield stress times by the bar forces. And then the constraints on that is basically just nodal equilibrium at each of the nodes. So just the forces in the x and y directions if you're looking at a 2D sort of planar problem, or sum to zero, or the external force that's applied. But how does this compare to the slab problem? Well, as you recall, I mentioned it was a rearrangement of the truss layout optimization problem to take into account self-stress rather than this externally applied loading. So we removed the externally applied loading constraint and instead add this imposed self-stress constraint. So again, minimizing the volume, subject to nodal equilibrium, but we add this self-stress. And that makes it directly comparable to what we would do in the slab optimization problem, which is minimizing the energy, which is the bar forces in the truss layout optimization problem become rotations, so Q becomes D. The length over the yield stress just becomes the length times by the moment capacity. Again, we have an equivalent to the nodal equilibrium is actually nodal compatibility, and the equivalent to the imposed self-stress is an imposed unit displacement. So virtual work is being taken into account there. But the key thing to all of this is that the mathematics for both problems is quite easy to solve, and computationally we can therefore solve quite large problems quite quickly, and that's what allows us to be able to undertake this optimization and identify these complex critical collapse mechanisms. So you can see here both are simple linear optimization problems. Just a little bit about the compatibility constraint. So if we have a node here that is at the end of 5 potential slip lines, all we're saying is that the sum of the rotations in the x and y directions must come to 0. So basically you're stepping round the node and adding up the rotations, and once you go all the way around in the x and y directions, you must come back to the same point as you started. And one thing is that obviously the compatibility is explicitly enforced at the nodes numerically, but also at the points where these potential yield lines cross each other, then it's implicitly enforced at those points also. So you can identify quite complex failure mechanisms with crossing yield lines and be confident that the compatibility is all okay, even though there's no node at that crossover point. So if we have a quick look at some of the examples in the literature, this first one here is basically a fixed square slab problem, and we're modeling just 1/8 of it. It's got fixed supports. The solution we can see is 42.851, and that's from a 1974 paper by Fox. If we solve using our method, which we call discontinuity layout optimization, then using quite a full nodal density, we get to within 4 significant figures. So only the last one here is different, so 0.1% higher. And what we found was actually if we solve the problem with more and more nodes and then extrapolate the line, then we come to exactly the same solution as Fox had found in his paper, so 42.851. So the more and more nodes we put at it, we can see that eventually we would get to the same solution. So that's giving us some confidence in the method that it's actually giving us the right solution analytically. The second example is a more sort of practical indented slab problem that was presented by Jackson in his PhD thesis from Cambridge about 5 years ago. And as mentioned, it's got an indent in the corner here, and it's also got combinations of different support types. So we've got obviously fixed and also simple support types evident. His solution was 29.2 for this, and you can see actually that our DLO solution, the best that we got, was actually slightly lower than his solution. The trade-off being that the mechanism that we identified using discontinuity layout optimization is actually more complex than the one that he had presented previously. So there is some trade-off in geometrical complexity if you're wanting to look at getting slightly more better or accurate solutions. One thing that we have been considering, and if there's enough call for it from users of the software, is actually allowing, once the problem has been solved, users to simplify the solution so that it can be checked against hand calculations, for example. So you can see on this slide that we've got our DLO solution actually slightly simplified in A, but with higher and higher factors of simplification going towards F. And what that does is you can obviously apply this simplification factor, and eventually you'll come to a point where the problem mechanism is simple enough that you could go away and then check the solution by hand, just to make sure that you have, again, extra confidence in the method. And then thirdly, the last sort of literature example that we'll look at is an apartment box. So it's quite a realistic example, and it was something that was mentioned quite a lot in the Concrete Center guide due to it having a complex shape with quite a lot of blade columns both internally and externally, and an irregular sort of geometry around the outside. And like I say, this is from the Concrete Center guide, which was written by Kennedy and Goodchild in 2004. So you can see here there's a lot of potential failure mechanisms that, if you were undertaking a sort of standard yield line analysis by hand, you would spend quite a lot of time looking at and deciding which is the critical case. And in order to account for the uncertainties, because obviously if you're doing a yield line analysis, you've got to postulate a failure mechanism that is as close to what would actually be in existence as possible. But in order to take account of the uncertainty in this, the design guide did suggest that a margin of safety in this case of 15% was applied to account for this potential inaccurate mechanism. But you can see on this slide we set up the same problem using LimitState Slab, and within I guess an analysis time of a matter of seconds, we identified this quite complex critical collapse mechanism, which is involving the left-hand side of the slab with quite a few fan mechanisms around the blade columns. So you can see that the software can be applied to sort of quite simple problems and also quite complex problems equally as quickly and efficiently. So what I could do now is actually take you on to some examples of using the software. So if I just bring back the interface, and we'll start again. So I think initially the best thing to do is probably just explain a little about the interface for the software. So I will just set up a standard rectangular slab problem that we've taken from a wizard, and you can see in the user interface we've got the main viewer window here, and everything is fully interactive, so you can click on different aspects of the model, and in the right hand side here there is the property editor, and anything that you click on will be reflected in this property editor, so you can see the different properties that you can then modify. So if I click on a solid, which is the slab, you can see that we have a nodal spacing, which is defining how tightly packed the nodes are, and also what the slab definition or the material is for that solid. Similarly, if you click on a boundary, you can see what the support type is, and also what the spacing of the nodes is. So that's the user interface and the property editor. You can see also that the interface has a standard menu system and also a set of toolbars for undertaking different things, and they're all color coded so that you can easily go back to using the right thing. So the green buttons here are for viewing, the purple buttons are for adding loads, we've got the blue buttons down the left hand side here which are for drawing, and then the red ones which are for performing functions with the cursor, so sort of panning, rotating, things like that. And it's very easy just to, for example, turn on the grid, draw another part of the slab, delete it. So you can very easily change the geometry and undertake, I guess, what if type analyses. And lastly, we have on the left hand side here the list of slab definitions, and you can see there's 3 built-in slab definitions already. If I click on any of them, you can see the properties of them, and it's all in terms of the MP and the angle at which that MP is acting, and you can have it in 2 directions as well as specifying a thickness and a unit weight. So you don't necessarily have to stick to a 90-degree rebar layout. So what we'll do is actually set up and solve a problem quickly. So if I go start with an empty project as we did previously, actually what I'll do is I'll start with a rectangle. That's probably the easiest. I'll go through the wizard system. So we can see here I'll keep the width and the height of the slab as normal, so 5 meter width, 4 meter height, and a 0 skew angle. If you wanted to add a skew angle in, obviously you can, and the wizard will generate the geometry for you based on that. Also need to add some support types, and in this case what I'm going to do is make all of the supports simple. There are a number of different support types. You've got free, fixed and simple, which are sort of the obvious ones, and also a symmetry boundary which acts as basically like a mirror, so you don't have to then assess the entirety of a slab if you know that it has lines of symmetry in it. And if you remember back to the first example problem that we talked about earlier, that used lines of symmetry to split down a square slab into an eighth so that we could analyze that with more accuracy. But in this case we're going to have all the boundaries are going to be assigned a simple boundary type. So we've got the geometry in there. Now we need to look at the materials or the slab definition. In this case, what we want to do is create a new slab definition, and I'm going to call it slab. Change the color so we can differentiate it from the ones that are actually built in, and then we've got the properties of that slab definition on the right hand side here. And as I mentioned previously, the way in which the software works is to specify hogging and sagging values for MP and an angle to the horizontal at which that acts. So you don't necessarily have to have like I say, a square grid layout, you can have any angle you want between those. Also, if you're wanting to take into account the self-weight of the slab, then you can specify the thickness and the unit weight of it. But in this case, I'm going to leave them as 1. So we set up a geometry, we set up our material properties. The next thing we need to do is add some loads. So a load case in the software is basically a combination of a partial safety factor set and some amount of loading, and the loading can either be as a pressure or a self-weight, a line load or a point load. And the partial safety factors, by default everything is set to unity, so the adequacy factor is a straight multiplier on the applied loading that you're saying you want to factor up. But similarly, you can also create new partial safety factor sets where you can see here you can specify different values for permanent variable and accidental loading, as well as factor the material strengths. But we're not going to do that in this case, we'll just keep it as unity. And then lastly, we have the analysis tab, and all that does is set the nodal density. So we see here we have a number of built-in options ranging from coarse to very fine and custom. So if I set it to coarse, the number of nodes that the problem tries to use is 250. If I set it to very fine, it's trying to use 2000 nodes. So it's trying to make a denser nodal grid within the problem. So obviously then there will be more potential yield lines, and therefore the solution will be more accurate. Generally what we say is if you keep it on the medium nodal density, which is 500 nodes, then you should be able to use that to get a quick solution for sort of scoping out your problem, and then when you want to get a more accurate solution, then you would increase the number up to maybe 2000 or possibly more. So we've gone through the wizard, we set up all the different things that we need here. So we've got, again, the geometry, the materials, the loading, and then the analysis options. If I click finish, we'll just get a quick tips that would get shown, but we can OK that. You can see that our problem has now been set up. So if I solve that, what you see is within a few seconds we get the standard envelope failure mechanism type, and also the yield lines are displayed on it for you to see. So we've got the red, which is the sort of sagging yield lines, and the blue, which is the hogging. And the thickness of these yield lines is proportional to the amount of rotation you get. So what happens is it's quite sort of even in this case, but in other problems you can get yield lines that are thicker and thinner, and that will give you an impression of where the most movement is happening within your slab as it's failing. And you can see the adequacy factor on the applied loads in this case is 1.22, so saying that we are multiplying up the units pressure load by 1.22 in order to cause collapse. And as previously, you can animate the solution and then view it in 3 dimensions to get a better understanding of exactly what the collapse mechanism is like. And obviously you can use the slider up here to move it backwards and forwards to any position that you would like. If you take it right back to 0, then you get back to the original yield line mechanism. So we've done something very simple. We've just got a rectangular slab and solved it. But one of the beauties of the software is that you can change things very quickly. So if I unlock it, I can then, for instance, make the slab definition orthotropic. So if you remember previously, we had MP of 1 for hogging and sagging in both directions, and those 2 directions were at 90 degrees to each other. What we can potentially do is, say, set the first MP values to 5 and then the second MP values to 1. So now the strengths aren't the same in both directions, and solve again and see what happens. And you can see that we've got, again, an envelope failure mechanism, but the horizontal portion of that has been stretched out to reflect the extra strength in that direction. Similarly, the adequacy factor has moved up from 1.22 to 3.77, so we've got quite a much stronger slab because of doing that. So you can see we can change the material strengths. Another thing we might want to do is add a column, and it's quite simple to do that. So just using the blue drawing buttons on the right here, we can add points for a column, and I'm going to add them from 2.2, 1.9, to 2.4, 2.1, so a small square column in the center of our problem here. And all we need to do to actually make that into a column is then to delete the center of the solid and set the boundaries to either be fixed or simple. In this case, I'm going to set them to be fixed and solve the problem again. And you can see now we've got a fan type mechanism occurring around the column, and then sort of an extended envelope around that. Obviously, the more nodes that we put into the problem, the more refined that failure mechanism would be. You can see here the adequacy factor for this case is 2.87, so that's an increase from the 1.22 that we had to start with, which you would expect by adding this extra support from the column. If we moved up to a very fine nodal density rather than using the medium, then the value for that would go down to 2.82, so you get a reduction of maybe about 10%. So if we unlock now, another thing we might want to do is look at the boundary conditions. So again, it's very simple to just change those. I've selected these two on the right hand side here and take them from being simple to being free. So now we've got this nice free edge at the right hand side there. If we solve again, you can see now, because of this reduction in the support at that right hand side, we've moved away from the sort of combined fan and envelope failure mechanism type to one where the right hand side is drawing the failure mechanism towards it, and that's reflected in the reduction in the adequacy factor down from 2.87 to 1.51. Lastly, for this one, I think again what you might want to do is add another column on the right hand side, potentially to add an extra bit of support. So what we can do is exactly what we did previously, is just add this column, some fixed supports, and solve again. And you can see we go back to this fan type mechanism with sort of a combined envelope around it, and the solution has increased from 1.5 to 2.88. So adding that extra column in is actually showing that you can increase the load by almost double. So that was quite a simple rectangular problem. The next thing we might want to look at is a slab of some sort of arbitrary geometry. So what I'm going to do is just start with an empty project like we did earlier and draw myself a random slab shape. So in this case I'll make it into a cruciform slab. So we've got this cruciform shape made by drawing the polygon. If I select all of it, and then in the property editor, the external boundaries, I can set the support types to be simple. So we've got our geometry and our boundary conditions, and we could add unit MP concrete to it. So that's saying that in both directions, the hogging and the sagging MP values are unity. We can also add a unit pressure load. So if I select all, we'll add this unit pressure. And you can see that's reflected if I turn the grid off and zoom in. We've got this red line around the outside just to show that the solid now has a unit pressure load or some sort of pressure load added to it. So we've got very quickly all the constituent parts of our problem. We've got the geometry, we've got the boundary conditions, we've got the loading, and we've got the material. So we can solve. What we see is we get this quite nice failure mechanism, and with an adequacy factor of about 11.73. Again, we can animate and query that failure mechanism just to get a better idea of how it is failing. Something else that you can also do is, if you wanted to then take this away and show to a colleague or a client, you can generate a report. So if you go to analysis and report, once the problem is solved, you can see that you can select the different sections that go into the report, and once you click OK, the software will generate that for you. So you get a summary at the top telling you what the adequacy factor is, also presenting a picture of the critical failure mechanism, and then it will explain the geometry and all of the different material properties and partial factors and loading that you've applied to it. But if we go back to the problem itself, so we've generated this user-defined geometry here. But what we might want to do is start to play about with it a little. So maybe if we want to see what happens if we, instead of having simple supports around the arms, we make those free and then just add columns in the corners of the center. So we can very quickly do that just by selecting the boundaries using this rectangle select, set the boundaries to free, and then what we want to do is add these columns in. And as you saw in the previous example, it's simply a case of just drawing these rectangles, deleting the centers, and then setting the edges to have some sort of support conditions to them. Oops, sorry. So I can delete those, select them all, and then if I set those boundary conditions to be fixed, we can solve that and see what type of failure mechanism we get. So you can see it's changed quite dramatically from being the sort of envelope type failure mechanisms to just being these straight lines. And again, we can animate it and see what's happening there. But we might also want to make the slabs bigger, so we can also do that. It's very simple. So if I just select that side and just drag it across, oops, sorry. You can see that you can snap to the grid, which makes moving parts of the structure around very simple. So now we've gone from having quite narrow arms to our cruciform slab structure. We've made them quite large, so we can solve again and see what happens to the failure mechanism. And now the columns in the corners are having a much greater effect, and you've got this sort of rose petal shaped failure mechanism, which is quite interesting. And as you may recall, I mentioned that the rotations are reflected in the thickness of the yield lines that are displayed on the screen. So you can see here that the main yield lines are the ones that are going to the center and around the outside, whereas you've got the sort of lesser ones in the middle. And if you animate, you can see that that's pretty much what's happening there. So you've got the main rotations around these edges and then leading into the center, whereas the rotations in the sort of spider web pattern in the middle is a lot less. And again, the adequacy factor here has changed to being 2.48, whereas previously it was about 3.2. So the larger slab, obviously, the effects of the pressure loading are increased because of the increased distance between the supports. So you're getting a reduction in the adequacy factor as you would expect. So we've had a look at a very simple problem, we've had a look at a more complex problem, but one that's admittedly a little contrived. The last one that we could look at is something that is a little more realistic, and that would be a problem that involves an apartment block. So what we can do is actually import the geometry from a DXF file. So you can see here I've already created a DXF file. It's quite a simple one that just outlines the columns and the slab layout of my building. If you click the import, then you get to choose which layers in the DXF that you want to actually use in the problem, and once you click OK on that, it will take any sort of closed loops within the DXF file and make solids out of them for you. So you can see I can select all of these separately. And then once you've got this geometry in, which would probably take quite a little while to generate if you're doing it within the software, but using sort of CAD software, you may already have the file available, or you can generate something quite quickly. You can import it. Then the process would be the same as previously. So you would go through it and add support conditions and different types of material properties, and your loading, you could apply all that. And then what I'll do is I'll actually open a file. If you bear with me a second. So you can see here that it's the same problem, but now we have the material properties applied to each of the different zones. So you can see the columns are supporting it. There's actually no support around the edges to speak of, and we've got separate material properties for the different parts of the structure. If we click on the loading, you can also see where the pressure loading is applied, and if we wanted to apply sort of point loading in different positions, we could also do that. Then you come to solve, and again within a matter of seconds you get a critical yield line pattern and an adequacy factor on the applied loading. In this case it's quite a low adequacy factor. I've been a little worried about being in the apartment myself, but yes, you can see the failure mechanism is quite a complex one that you wouldn't necessarily have identified if you were doing it using a hand analysis. So we've gone through a few different examples there. So a simple sort of rectangular slab that's been built up using the inbuilt wizards in the software, a cruciform slab that we've generated ourselves just by drawing on the screen, and lastly a more complex apartment block problem that we have imported the geometry using a DXF file. And these are the sort of three different ways that you would generally set up your problem. So I'm conscious that we're almost out of time now, so what I'll do is I will see if there are any questions. Well, actually, I'll go through some conclusions first. So the Yieldline method obviously provides quite a powerful means of analysing the ultimate collapse state, but there's been over the past few years a lack of general implementation, such as finite element gives to the nonlinear, the elastic analysis. So we developed the Yieldline method we developed discontinuity layout optimization method and used that to automate the Yieldline method, which is typically involving a linear optimization problem, which is easy to solve, and it allows you to identify fan type mechanisms automatically. The software LimitState Slab is actually available now from our website, www.limitstate.com, if you would like to download it and give it a try. So I'll just move on and see if we actually have any questions from anybody. So if you bear with me a second. Yeah, I have one. Do we need to calculate the plastic moment capacity first and add in the input to check the adequacy factor? So yes, the current version of software does require that you determine the MP value in advance, but this is something that we are looking at streamlining for future versions of the software, obviously to give it more applicability, certainly in the design arena. Let's just scroll down. If the slab thickness is different in different panels, how will this software work? And actually next to it there's another question which is sort of related, which is, can the slab depth be varied linearly across its span and width? So for different thicknesses you can simply generate different zones within the software when you're building up your model and allocate specific material properties or slab definitions with different MP values and different thicknesses to it. And then moving on from that, the linearly varying slab thicknesses, you could create a number of strips and then use the method just described to approximate the change in depth and MP value. So you could add as many as you'd like. Alright, just have a look. How do we apply bridge-specific loading? Is there a predefined library? So you can apply point loads to represent wheel loading from vehicles and move these across the slab together, which would give you a good representation of the vehicular loading. There isn't actually currently a built-in library of loading for different vehicles, but it is quite easy to replicate them yourself. And actually, in fact, we covered this in a previous LimitState Slab webinar on bridge assessment, and you can actually view this on our YouTube channel, the link for which would be youtube.com/LimitState software. You'll also find the links to that video or any of our previous webinars on the LimitState website at www.limitState.com/webinars. So I'd just like to say thank you to Matthew and thanks to everybody who's been attending today. We do hope that you found the webinar informative. As mentioned at the start, obviously if you have any questions that we haven't answered today, please do get in touch via info@LimitState.com and we'll get back to you straight away. As I mentioned, LimitState Slab is available to download or purchase now from our website, which is LimitState.com. And we'll also be in touch over the next few days just to get some feedback from you and find out if you do have any further questions. Lastly, please do look out for our other webinars which deal with LimitState Slab and all our other software products, and we'll be just sending out event notifications in advance of these, but they will also be posted on our website at LimitState.com/webinars. So lastly, I'd like to say again, thank you all for listening. Hope you can join us again for one of the future sessions. Look forward to speaking to you then. Goodbye.